Hello, I am Arnab Bhattacharya. I am a faculty in the Department of Computer Science and Automation at the Indian Institute of Science. So, today I am going to tell you about high dimensional geometry and its role in computer science. Let me start with an introduction. So, getting a good grasp of high dimensional geometry is increasingly becoming important in understanding modern developments in computer science. This is because of one key reason: data sets and models for representing data are increasingly being represented as long vectors and matrices. Let me give a few examples. You can take a image. So, this is a 512 by 512 pixel image. So, that corresponds to a vector of length 2 to the 18. This is often the representation in which this image is fed into image processing algorithms. You can take a document. A very useful way of representing documents is in a bag of words model, where basically you record the number of times each word occurs. You keep track of the count of each word. The English vocabulary is of size about 2 to the 17. So, that creates a vector of length 2 to the 17. You can take neural network. So, neural network or any really machine learning model, what it does is it takes in data and it represents it in terms of some parameters that it learns. So, it creates a feature vector representation of the data. So, the number of parameters in a typical deep neural network nowadays is about on the order of millions, which is 2 to the 20. So, all these different paradigms create vectors and other objects in high dimensional space, and geometric techniques are very useful for dealing with these data sets. Why geometry? There are two key reasons. One is that if you view data sets as vectors or objects in high dimensional geometric space, then we get access to familiar tools from geometry. You have notions like angle and distance, which can capture concepts like similarity or dissimilarity between items, operations like projections and rotations that you can apply on data sets. Then relationships like subspace and linear dependence relationships, which is again useful as a geometric primitive. There is another computational reason. Modern computing infrastructure, specifically GPUs or graphical processing units, accelerate matrix vector multiplication. Okay. So, it is specialized hardware designed to accelerate matrix vector multiplication. So, because of that reason also it is very useful to have data sets represented as high dimensional vectors. But there is a counterpoint to this. Although we do have access to notions from geometry like angle and distance, as I mentioned, typically we learn these concepts in the realm of low dimensions, in 2 or 3 dimensions that we experience in daily life. Whereas, these vectors that I told you about reside in high dimensions, 2 to the 20, 2 to the 25 or higher, and high dimensional geometry turns out to be very counterintuitive. So, in the course of this talk I will give a few examples where you can see this happen. Good. So, let me give an overview of the rest of the talk. So, in the next part of the talk I will describe one broad set of tools which go by the name concentration of measure. So, there are many different particular techniques which fall in this area, and I will talk about a few of them, and then we will try to apply these tools in the context of two applications. The first application is clustering of high dimensional data sets, and the second application is dimensionality reduction. So, let me talk a little bit about concentration of measure. Concentration of measure is a remarkable phenomenon. What it says in essence is the following: that every well behaved function, well behaved in a certain sense, defined over a high dimensional space is actually nearly constant nearly everywhere. This is obviously not true in low dimensions. We have well defined functions which have lot of variation, but in high dimensions it turns out that functions are nearly constant nearly everywhere on their space. So, a very concrete instantiation of this philosophy is Levy's lemma, which I will state in the following way. So, on the left hand side you see a sphere. This is a sphere in n dimensions, it is denoted by S n minus 1, and you have some function which maps from the surface of the sphere to the real numbers, and we will assume this function is well behaved in the sense that this function is Lipschitz, meaning that if you take the value of the function in two nearby places, then the value of the function also differs by a little bit. This is the standard notion of Lipschitz test which one studies in real analysis. And suppose x is some vector which is drawn uniformly from the sphere. So, you just pick x uniformly from the surface of the sphere, and let m of f be the median value of f on the sphere. Okay. Then Levy's lemma says the following, that actually the value of f differs from the median by more than epsilon, okay, on a negligible fraction of the sphere. So, there is only some small amounts here denoted by red. So, in these regions of the sphere, the value of the function differs from the median value by epsilon amount. On the rest of the sphere, the function value is within epsilon of the median value. This is remarkable if you think about it. What it means is that the sphere in high dimensions does not actually look like this picture. So, the equator of the sphere is very fat. So, it contains most of the volume, okay, and the poles such as the regions denoted by the red are actually very spiky, okay, because they contain a very small amount of the volume of the entire surface of the sphere. But then you have to remember the sphere is rotationally symmetric. So, what this means is it is somehow spiky in every direction, but it is very fat around the equator, okay, and the equator also is of course rotationally symmetric. It is something we can't really visualize even properly, but this is a fact that that if you look at any continuous Lipschitz function on the sphere, then it really is nearly constant nearly everywhere. So, although Levy's lemma particularly is for the sphere, this phenomenon extends vastly to like a vast number of settings. Let me give one other instantiation. This is called the Chernoff bound, and this is very useful in computer science in many different places. You can think of it in the following way. So, suppose you have a fair coin, okay, and you toss it n times. The first time you toss head, the second time tail, and so on. Okay. Now, again, as I said, it is very useful to represent data as a vector. So, I will do the representation in this way. So, the first toss, if it is head, I will say it is +1, if it is tail, it is -1. Similarly, for the second toss, third toss, up till the nth toss. Okay. So, now you have a vector, a +-1 vector of length n. This is a valid vector, and suppose the question I want to ask is how much does head beat tails? Okay. How many more heads do you get than tails? I can formulate it in the setting of Levy's lemma. So, if you look at like any +-1 vector of length n, it has a norm root n. So, it basically lies on a sphere of radius root n, and what I am looking at is just the sum function, the sum of x1 through xn. Okay. So, if there are more heads than tails, this will be positive. If there are more tails than heads, this will be negative. If the number of tails and number of heads is exactly the same, f of x is going to be 0. Okay. Now, what Levy's lemma says in this context. So, here I am not looking at a function over the entire sphere, I am only looking at a function defined on the +-1 points, okay, on the lattice. But again the same philosophy applies. F of x is always, nearly always close to 0, nearly always nearly 0. Okay. More precisely, one has the following statement that the fraction of +-1 to the n points where the value of f of x is more than t is at most e to the minus t square by 2n. So, what this means is that if t is say something like 10 root n, then mostly everywhere on the sphere the value of f of x is less than 10 root n. Good. And this again, this phenomenon I said for +-1 points, but it extends much more generally. Not only can it be on a sphere or the +-1 points, but really there is a notion called sub-Gaussian distributions. So, that if each xi is independent and sub-Gaussian and means 0, then f of x is again nearly always nearly 0. Okay. And even beyond. So, these are vectors, but the same phenomenon even applies to matrices. So, suppose you have some x which is a random matrix, this is just again an instantiation of the principle. So, if x is a random matrix with each entry being standard, normal and independently distributed, then the operator norm of x is again nearly always close to the mean value of the expectation of the operator norm. And more precisely, again, the norm of x is is very close to say 2 root n with good probability. So, so now I will go on and use this idea of concentration of measure to discuss two separate applications. One is clustering and the second is dimensionality reduction. All right. So, let me go to the first application, clustering. So, again, clustering is a very basic problem in data analytics. One has points in high dimensional space and you want to partition these points into well separated distinct clusters. Okay. Again, in low dimensions, like for example, if we look out of a telescope and see the stars, it's I mean there are ways to we can easily visualize the data, because for telescopes we can actually see the data, and if the data resides in low dimensional space, we can see it on a computer monitor say and see points in low dimensional space, and we can visually organize the points into distinct clusters. But this problem becomes a huge issue in high dimensions, where really there is very little way to visualize the space. We have our intuitions about high dimensional spheres and cubes go haywire. So, it is a basic problem then in data analytics. Once you have these, once you have data represented as high dimensional points, how do you really cluster them? So, really in order to give you a formal to talk about it a little bit precisely, I will tell you about a model that mimics a possibly real distribution. So, this is called the Gaussian mixture model. So, here what you have is, suppose there is some number, some vector mu, which is a point in R n, a high dimensional vector, and you have two clusters, one cluster around mu, the other cluster around minus mu, all right. So, with probability half, the point is a point in n mu I n, which means that it is a Gaussian distributed point with mean mu and covariance matrix identity. Okay. And similarly, with probability half, it is a point x in n minus mu I n. So, it is so the with probability half is its center is minus mu and the covariance matrix is I n. Okay. So, so suppose this is a model and we really want to find out what mu is. Okay. This is a toy model which can mimic the real distribution, but even here in high, there is really no good way to visualize it, because if you project this into low dimensional space, then the cluster representation gets lost if you do not know the right value of mu. So, one can do what is called a spectral analysis. So, there what you have so there the actor, the main character in this analysis is the covariance matrix. Okay. So, so again x is the random vector which is chosen according to this distribution, and you can define the covariance matrix sigma to be the expectation of x transpose. And a very sort of basic idea in data analysis of high dimensional sets is the following. It goes by the name of principal component analysis (PCA), which says that the largest eigenvalues of sigma of the covariance matrix are the directions of largest variance in the data. Okay. So, for example, if you have some data set like this, so visually we can see that it is more spread out in this direction and less spread out in the perpendicular direction, and the eigenvectors of sigma precisely actually captured this phenomenon. Okay. So, the largest eigenvector of sigma is the vector u1, which is in this direction, and the second smaller the second largest one is this one, which goes perpendicular. Okay. So, if we can somehow capture the largest eigenvector, then we can get the direction in which the variance is the largest. So, this is the idea that we can use, and this is called the spectral clustering algorithm. So, this can work with the Gaussian mixture model. So, again you have points x 1 through x m in R n. So, these are samples that you get from the mixture model. With probability half it is in one cluster, with probability half it is in the other cluster. And now, what we want to output is we want to output a partition of the data set into two clusters. Okay. So, what you do is, of course, we do not have access to the actual covariance matrix because we do not know x, but we can compute a sample covariance matrix, which means that for every xi that you sample, you look at xi transpose and you take the average of those. This is called the sample covariance matrix. Then you can compute the largest eigenvector for this sample covariance matrix sigma m, then based on that eigenvector you can partition the data set. Okay. So, V is the eigenvector of the is the largest eigenvector of the sampled covariance matrix, and then what you do is for each vector you look at whether V falls on whether x I falls on the right side of V, or so whether the angle between x I and V is acute or obtuse. So, if you do that, right. So, let us see what happens. So, it is actually quite simple to see. So, so again this sigma of x, which is the covariance matrix, this is the identity matrix shifted by mu transpose. So, mu again is the direction is the separation between the two clusters. So, this mu transpose will be added will be affecting the largest eigenvector. Okay. So, the first step in the algorithm, remember, is to compute the sample covariance matrix. Okay. So, again due to concentration of measure, the phenomenon that I told you about, you can show that the difference between the sample covariance matrix and the actual covariance matrix is small. Okay. So, the difference can be measured by the operator norm, and this is small again due to concentration of measure. So, now I have some sigma m which I can claim is close to sigma if m is large enough, and now I compute the largest eigenvector of V. Okay. So, the eigenvector of the real covariance matrix sigma is this blue arrow. So, it is going in the direction of the separation, right, and now I compute V, which is the largest eigenvector of the sample covariance matrix. So, this is this red arrow. So, as you can see, V and sigma are not exactly the same because of sampling errors, but because sigma m is close to sigma, you can use what is called perturbation theory to show that V is also close to mu, okay, in angle. Okay. So, the angle between V and mu is close, and then that that implies that the partition induced by V, that is I look at whether points are have an acute angle with V or obtuse angle with V, that is correct with good probability. And the sample size m, which is required for all these claims to be true, is actually only linear in the dimension and polynomial in the accuracy parameter 1 over epsilon and 1 over the length of mu. So, as you can imagine, if mu, the intercluster separation, when it becomes smaller and smaller, the problem becomes harder and harder because the balls are closer and closer to each other. So, here we have an example where we can take ideas from concentration of measure and ideas from geometry to actually solve a very basic computational problem in data analysis. So, I am going to move on to the second application, which is dimensionality reduction. So, this is also a very useful primitive in visualizing and understanding data. Often it is the case that although the data resides in high dimensions, right. So, you have a picture which is ostensibly represented as a high dimensional vector or a document which is represented as a huge vector, the vector really has some underlying structure. Like for example, in a document you do not have all the words in the English vocabulary occurring there are only a small number of words, and maybe some words like is or are they are much more often than other words. Okay. So, the data has some underlying low dimensionality hidden inside it. Okay. And even if not, there is a way that one can compress data, so that important information about the data is preserved. Okay. So, we do not need to work directly with the high dimensional data. So, once we have high dimensional data, we can use the geometry of the space to actually compress the vectors. So, let me give an example of this, a very sort of stark example which drives home the point. So, this is called the Johnson-Lindenstrauss lemma. So, so I will describe it in words. So, suppose you have n points, okay, and these n points can be in very high dimensional space, I do not really care. Now, these are some arbitrary points, but what this Johnson-Lindenstrauss or JL lemma says is that there is a way to map these n points into a space of dimension log n. Okay. So, log n can be much smaller than the ambient dimension d. Okay. So, there is a way to map it into this log n dimensional space such that the the pairwise distance between the points in the original data set and the projected data set are approximately the same. So, this means that if you care about distance as a notion of similarity or dissimilarity between items, then that notion is preserved even under this low dimensional projection. So, let me just be a little bit more precise. So, you have q, which is a set of n points, and k is the target dimension to which you are projecting. So, as I said, it is proportional to log n. So, it is really proportional to log n over epsilon square, epsilon is a parameter. Then there exists a linear mapping, it is really a linear projection in the way that you learned about in linear algebra, such that for all pairs of points u and v in the data set, the distance between f of u and f of v, which is the projection of u and a projection of v, is within a factor of 1 plus epsilon of the original distance between u and v, and this applies to any set of endpoints. Okay. So, any set of endpoints can really be brought down into a space of dimension log n. So, although the ambient dimension can be large, there is a way of compressing it which preserves useful information. And I mean, I can even tell you a simple algorithm. There are many different algorithms to realize this lemma. One is the following. So, you apply a random rotation to the points in the space. Okay. So, you take the points, you rotate it in a random way, and then you just chop off the vector representation. So, you only look at the first k coordinates of each vector. Okay. So, there are totally d coordinates because these are in d dimensional space, but I just ignore the last d minus k coordinates and I only look at the first k coordinates. So, this I claim is actually enough for you to preserve pairwise distances. Okay. I do not really have time to explain the proof in full, but let me give you a proof idea which again harks back to the concentration of measure phenomenon that I told you about. So, this is just the following. So, if you have a random point on the sphere, okay, and I look at the sum of the squared, so I look at the norm of the vector restricted to the first k coordinates. So, this I define to be f of x. F of x is x1 square plus x2 square all the way up till xk square. So, only look at the first k coordinates and I look at the sum of the squares of the coordinates. Then because f is Lipschitz, you can check, you can use Levy's lemma, which says that this function f is nearly the same on almost all of the sphere. Okay. Amazing, right. So, it says that this function actually takes nearly the same value, which means that if I have the original data set and I apply a random rotation, that means that each pairwise the difference between any pair of points, I can think of that as a vector, and that becomes a random point after the random rotation on the sphere, and the length of that difference vector is preserved because of this concentration of measure phenomenon, and that is why this algorithm which I described works, right. Again, this is a very sort of this idea comes from properties very unique to high dimensional space. Okay. Something like this will not work in low dimensions. There are many further developments along these lines. The algorithm which I told you about is not particularly efficient. Why? Because you need to apply a random rotation, okay, and applying a random rotation to a very high dimensional space can be expensive, but there are ways to actually make this fast. So, the projection matrix, the matrix which takes the d dimensional vector and projects it into k dimensions, that itself can be made sparse, which accelerates the algorithm. So, this is a line of work which has been continuing over the last 10 years. Then what I told you about the JL lemma applies to all data sets, okay, but it could be that because of the particular characteristics of the data set, it is possible to embed, it is possible to project the data set into a space of even lower dimension than log n, and indeed that is true. So, there is something which is called the Gaussian width of a data set. It is a purely geometric concept which captures the embedding dimension. So, the minimum dimension to which a data set can be embedded, so that the pairwise distances are preserved. And finally, there is a huge amount of work a little bit spurred by the developments in machine learning on nonlinear dimension reduction. So, here suppose for example, the objective is more complicated than pairwise distances. Perhaps you care more about pairwise distances between some pairs of points than other pairs of points. This could be motivated by a particular application. Okay. In these cases often linear, so the projection linear projections need not be enough, linear projections need not satisfy the objective that you care about, and one may need to go to non-linear dimensionality reduction techniques. Okay. This is an area of research under hot topic of research right now. Things like autoencoders are non-linear dimensionality reduction algorithms. So, I will try to wrap up now. So, I will conclude the talk. So, in conclusion, finding hidden structure in high dimensional data is a recurring and important theme in computer science. So, we saw in the first application where the hidden structure was the clustering, the second application where the hidden structure was a low dimensional embedding of the data set. But finding this hidden structure is very important, because it gives us a better handle on what the points are supposed to be representing. Okay. For example, if the vectors are representing images, maybe points which belong to images of animals are very different from images which from the vectors which correspond to images of plants. Okay. So, one can use this idea of this theme of hidden structure occurs repeatedly in learning and computer science generally. Okay. The other thing I want to emphasize is that human intuition about geometry and optimization landscapes in high dimensional spaces can be very off. Okay. So, in this case one needs recourse to mathematical statements, and there is a whole body of mathematics called functional analysis, which has been looking at these problems since the 1800s, and those kinds of those theorems from that area are very much in vogue in computer science right now. Yeah, so mathematical machinery and efficient algorithms for high dimensional data is one of the most active areas of research currently. With this, I would like to end the talk. Thank you for your attention.